Good morning, students. Let us start the class. In the previous class, we were discussing about how to model a transistor in a linear fashion around the Q point. And please recall that we are discussing the small signal operation where we presume that we are only working around the Q point itself, and there we assume the transistor's behavior to be linear because our operation of the Q point is happening only through an input signal which is of very small amplitude, a few millivolts, and sometimes even few microvolts, and because of which we do not consider the nonlinear operation of the transistor around the Q point. That is why we specifically say this is a small signal operation where we want to model a transistor in terms of the passive counterparts. We want to model the transistor in terms of its linear behavior. Otherwise, the completely non-linear behavior is very difficult to model. As I was telling you, if at all we have to represent a curve, a continuously changing curve, we require sometimes quadratic equation, sometimes cubic equation, and if you want more accuracy, we have to go for the fourth order equation, fifth order equation. That way it goes on. Or else we have to go for a differential equation, double differentiation, triple differentiation, because such processes are going to get into much minor details of the curvature. So all the nonlinear devices which we are dealing with in engineering and technology and science, they are all having their response in terms of the curvatures. That is why mathematics has to be effectively utilized along with engineering for the modeling of such behaviors. So here we presume, just for simplification, we presume that the transistor can be linearly modeled around the Q point, and we have seen a model called pi model where we have at the input side we have a resistance called beta into Re, where Re is nothing but the dynamic resistance of the emitter, and at the input side, as the current is beta times lesser than the emitter current, we can represent the same resistance multiplied by beta. So that is how in the pi model we have beta into Re at the input side, and at the output side we have Ic, because we presume that around the Q point the collector current is constant, so we represent it by means of a current source. So using that pi model, the amplifier circuits can be simplified for AC analysis. All the capacitors act as short. You already know X equals 1 over 2 pi Fc. So when F keeps increasing, Xc keeps reducing. After a certain frequency, we can actually completely ignore the value of Xc, because based on the value of the capacitance and the value of the frequency, Xc can be in milliohms and sometimes in microohms. So we are always dealing with the audio frequency range or radio frequency range. So in those ranges, many times we choose a higher value capacitance so that X equals 1 over 2 pi Fc. When F is large, when C is large, X is really very less, it can be ignored. So we represent a capacitor as a short circuit for the AC signals, and the power supply acts as AC ground. Please recall the concepts of AC ground which I had discussed earlier. When a signal comes all the way to the power supply itself is either a big battery or itself is a big capacitor there. So naturally, whether a battery or a capacitor, that is going to absorb all the variations in the signal. So for the input signal, power supply is always an AC ground. Hence, the voltage gain, the input impedance and the output impedance can be computed using the AC equivalent circuit. Now, when we model this transistor in terms of its linear counterpart using that pi model, or we also call it as Re model in future. So when we model it, all other components we know the base resistor or the collector resistor or the emitter resistor or the voltage divider resistors, all that we know, we can apply this particular equivalent circuit in place of the transistor, and without actually conducting the experiment, we can find out the voltage gain, we can find out the input impedance, and we can find out the output impedance. That is the purpose of this modeling. As I've been telling earlier, it is not possible to test all the circuits physically on our own, because we are dealing with sometimes tens of transistors, at times hundreds of transistors, but in the integrated circuits, we are going to deal with the millions of transistors. So it is not possible to test all these transistors physically. If at all we physically try to test all these transistors, our projects or our improvement in technology will become really very slow. If human beings are involved in testing all the circuits, then the process becomes really very slow. That is when we are utilizing computerized systems, so that the computerized systems can handle large amount of data and they can work at a much larger speed than the engineers, and that way progress in technology is going to be faster. So without conducting the experiment itself, we can find out the voltage gain, we can find out the input impedance, and we can find out the output impedance. And that is what is required for us. The procedure is as shown below. You can see this circuit now. I have shown it for this base bias circuit now. In the base bias circuit, at the base we have RB, at the collector we have RC, then we have a blocking capacitor at the input, we have a coupling capacitor at the output, and then we may have a load resistance at the output. This RL, for the sake of simplicity, we have represented it as RL, or it can be an input impedance of the next amplifier stage, or it can be a loudspeaker as well. It can be any other load at the output. We are representing it as resistive load RL. So whenever we use BJT circuits, always the load we represent using resistors, because we are dealing with current and voltage. So it is easy for us to represent the load in terms of resistors. But in the next module, we are going to discuss MOSFETs and JFETs. There we are going to represent the load as capacitor, because there we are dealing with the device which is not current controlled, but it is voltage controlled, and there is no physical flow of current into the gate of the MOSFET. So there we represent it as capacitor. But I will explain that in detail again in the next module. Whereas electrical engineers always use the loads as inductor, because they are dealing with transformers, motors, generators, and many such inductive appliances. So in the electrical engineering, they represent the load as inductance, whereas in the BJT circuits, we represent the load as resistance, whereas in MOSFET circuits, we are going to represent the load as capacitance. Please remember this. Now this base bias circuit, we want to perform the AC analysis for the same circuit. What we do now is, we represent this transistor by means of this pi model. You can see this here. Emitter is grounded. At the input, I have this beta into Re, which is the dynamic emitter resistance multiplied by beta. And at the output, at the collector, we have this IC. This IC is nothing but the collector current, which is constant around the Q point. So the complete transistor, we have written it using this pi model. Now, at the input, when the signal is coming, we are visualizing this capacitor as a short circuit, because it passes AC. Now the same signal comes here. You already know that the power supply is nothing but AC ground for the signal. So we can simply write this V in, and we can write this RB with respect to ground. As far as the signal is concerned, RB's other end is at ground. As far as we are concerned, we have done the DC analysis, and we know that the RB is at the power supply point. But for the AC signal, power supply is nothing but ground. So we can simply write this RB with respect to ground. At the output, again, at the collector, when the AC signal is coming, RC is again at ground. So we are writing RC with respect to ground. Later on, we are writing this RL, or whatever is the load resistance. Now look at this particular AC equivalent circuit. The complete amplifier circuit of base bias we have represented using an AC equivalent circuit, and we have represented the transistor as a linear model now. Now, using this AC equivalent circuit, we can easily find out the input impedance of the circuit. Look at this from the input side. If you see, RB is in parallel with beta into RE dash. So, Zi or input impedance to this circuit is nothing but RB in parallel with beta into RE dash. The value of RB we already know. The value of beta is given by the manufacturer. And the value of RE we can easily find out using the formula 26 millivolts divided by IE, as I discussed in the previous class. That 26 millivolts is nothing but the thermal voltage, and at 27 degrees centigrade it is equivalent to kT by Q, which is equivalent to 26 millivolts. Please recall all those basics. So we can find out this RE dash. We already know beta. We can find out beta into RE dash. And we already know RB. Without actually conducting the experiment, we are computing the input impedance of the amplifier. Similarly, output impedance of the amplifier is nothing but RC here, because from looking at the output side, if at all you ignore RL, if at all the load is not connected, let us imagine that way. If the load is not connected, then the impedance at the output side is only RC. So we can simply write Z0 equals RC. When the load has to be considered, we can write it as RC parallel with RL. Now look at this representation. It is easy for us to conduct the AC analysis. Now, ideally, any amplifier should have very high input impedance and very low output impedance and very high voltage gain and very high current gain and very large bandwidth. Please remember these 5 points. Ideally, any amplifier should contain very high input impedance, which means what? When there is very high input impedance, the signal can be very less in amplitude. This very high input impedance simply means that the circuit will not take much current from the input signal itself. That means the input signal can be in millivolt or microvolt or nanovolt or picovolt or femtovolt or zeptovolt or yoctovolt, attovolt, whichever way. 10 power minus 12 is pico, whereas later we have 10 power minus 15, 10 power minus 18, 10 power minus 21, 10 power minus 24. We are dealing with much minute, small signals. For example, imagine a signal is coming from the GPS satellite all the way to the Earth station. It can be in femtovolt or in attovolt. It may be 10 power minus 15 volts range, or it may be 10 power minus 18 volt range. And if at all a spaceship is crossing the solar system, imagine that way. If a spaceship is crossing the solar system, let us say after Uranus, Neptune, Pluto, it is crossing the solar system, it will keep sending the signals to the Earth. Now, that particular signal which is coming from the spaceship can be in zeptovolt or in yoctovolt, 10 power minus 21 volts range or 10 power minus 24 volts range. So, we are going to deal with the signals which are in the picovolts range or in the femtovolts range or in the attovolts range or in the zeptovolts range or in the yoctovolts range. Now think about that. If such a small signal is coming to an amplifier should not load the input signal at all, which simply means that the amplifier should have very high input impedance. Then the amplifier does not require any energy from the input signal. Whatever is the energy required for the working of the amplifier, the power supply itself is going to provide it. Power supply is there to provide all the power to the amplifier circuit. So ideally, input impedance of an amplifier must be really very high. Similarly, output impedance of the amplifier must be really very low. Why? Because at the output we have a load. We may connect the load as a loudspeaker, we may connect a load as another amplifier circuit, or we may connect a load as any visual device, we may connect anything. For example, you have all seen these visual equalizers in your music systems or in stereo systems. Whenever a song is being played, music is being played, you can see that orange color, yellow color, red color, and green color, blue color LED is moving. Those are all lights which are moving in accordance with the amplitude of the music. So there, what actually is happening, the amplifier's output is partially given to a display system itself. And there, when the lights are moving, it is called equalizer lights. And when the lights are moving, it is giving a visual indication of the amplitude of the music. So in such a case, the load can be anything. When the load can be anything, the power supply must be able to supply that much of current to the load. For that reason, the output impedance of the amplifier must be really very low. I am talking about the ideal amplifier. I am not talking about base bias. Please remember that. Any particular circuit will not have all the ideal characteristics. Later, we are going to combine all of them together to have our own required characteristics. Otherwise, I am not talking about base bias. I am talking about ideal amplifiers characteristics. Please understand that. So ideally, input impedance must be very high for an amplifier. Output impedance must be very low for an amplifier. Similarly, voltage gain must be very high for an amplifier, because we are going to deal with very small amplitude signals and we must have very high gain. Similarly, current gain also must be very high for an amplifier, because we are going to have a very weak signal at the input and we want a strong signal at the output. And also, ideally, amplifier should have a very high bandwidth, which means any input frequency range is there, the amplifier must be able to provide the gain. But as I told you, all these 5 characteristics which are ideal, they cannot be obtained just by one particular circuit. That is why we are dealing with many types of circuits. Anyhow, the bandwidth related analysis is going to be dealt with in module 3. There I will discuss more about the details of bandwidth. Let me come back to the circuit now. Okay, what is the question? The question is, can you explain why we need high input impedance? Okay, imagine this particular circuit itself, and imagine this Zi is, let us say, 1 kilo ohm. I am giving an example. This Zi is 1 kilo ohm. RB parallel with beta into Re dash. We get experimentally, or we get after our exercise, let us say Zi is 1 kilo ohm. Now think about the signal which is coming here. The signal which is coming here is looking into this amplifier circuit, and across there is that 1 kilo ohm. Just look at this circuit now. There is V in here. RB parallel with beta into Re dash is 1 kilo ohm. Now what happens? The AC signal has to pass through 1 kilo ohm, which means what? You find out the current, AC current now. AC current can be V in divided by that 1 kilo ohm. That means the AC current will be in milliamperes. Now think about V in, which is in picovolt. V in will not be in volts at all. V in will be either in nanovolt or in picovolt or in femtovolt or in attovolt or in zeptovolt or in yoctovolt, as I told you. Now from your mobile phone, if you are transmitting a signal and that is reaching the nearest tower or the base switching center or base station, now from your mobile phone at home, you are trying to make a call. Just visualize the radio frequency which is going out of your mobile phone has to reach 1 kilometer away, 2 kilometer away to a radio station. Now what may be the amplitude of the signal which is going out of your mobile phone, and what may be the amplitude of the signal which is received at the base station? There will be a heavy loss in the atmosphere, because in the atmosphere it is a free space where everybody is using the same thing. Where there is a loss of signal, there is interference, there is noise, there is distortion, all those things are there. Now naturally, whatever signal is emitted from the mobile phone, the same signal is not received at the base station. I'll give you one more example. Let us say you and your friend are talking together and you are adjacent to each other. Then when you talk to each other, you don't have to increase your amplitude of the voice because you are very near. Now imagine your friend is 100 feet away from you. If your friend is 100 feet away from you, For your friend to listen to your voice, now you should raise your voice amplitude. Let us say your friend is half a kilometer away from you. Now you have to shout at him. If at all your voice has to be reaching to your friend, you have to shout at him, because on the way signal is being reduced. Now think about a signal which is coming from a satellite. If a signal is coming from a satellite, think about this V in itself. This V in itself is coming from a satellite. And let us say the impedance of the amplifier is now 1 kilo ohms. This very weak signal, will it be able to drive that much of current into the input impedance? No. What we want is, we want the amplifier to work independent of the power of the input signal. The power of the input signal should not be reduced because of the amplifier. Okay, that is the basic idea here. If input signal itself is really very weak, when the signal itself is really very weak, input impedance has to be high so that the AC current can be negligible. We have a DC current here for keeping the transistor in Q point, but we don't want any input AC current. Why? Because our input signal is really a very small and weak signal. That is the purpose of having a very high input impedance. Conversely, at the output we want to have a very low output impedance, because at the output we are connecting our load. So naturally our power supply should drive that load. Even AC current from the amplifier should go into the load. Think about this collector current AC. That AC current has to go into the load, which means there must be enough current at the output. If enough current has to be there, from the power supply only, all that current will be derived. So output impedance has to be ideally very low. I hope you got it now. Let me proceed with the discussion now. So I discussed about the input impedance and output impedance. Now let us find out the voltage gain. The voltage gain AV is nothing but V out divided by V in. Now what is V out? V out is nothing but IC into RC parallel with RL. Collector current is there, IC, that is nothing but the AC current now. And we have that collector resistance RC in parallel with load resistance RL. So voltage is nothing but current into resistance. So current into resistance, we have done it. IC into RC parallel with RL. And at V in, at the input again, V in is current into resistance. That current is IB and resistance is beta into RE dash. We will not consider this RB here. We are only discussing the AC current. Please understand, we are discussing the AC current. We are not discussing the DC current. RB is a biasing resistor where DC current is flowing. Whereas RC, we have to consider the AC current as well, because there is a ground here. So AC ground here. So just imagine only this much portion. We will exclude RB from our gain calculation. So V out is IC into RC parallel with RL, and V in is IB into beta into RE dash. So here we know that IC is nothing but beta into IB. When IC is nothing but beta into IB, beta gets cancelled, and even that IB gets cancelled, and we will get AV equals RC parallel with RL divided by RE dash. Or in short, we can say AV equals small rc divided by small re dash. That is, capital RC is the resistor across the collector, and we have a load resistance. So just look at this formula. Zi is RB parallel with beta into RE dash, and Z0 is RC. AV is RC parallel with RL divided by RE dash. Now we know beta, we will be knowing RB, we will be knowing RC, we will be knowing RL, and we can find out RE, that is nothing but 26 millivolts divided by IE. IE we can find out by the DC analysis, and by means of this we can actually compute the input impedance, the output impedance, and the voltage gain for a given amplifier circuit. I hope you got it. Let us have an exercise on this now. There is a small note here. As beta into RE dash is much lesser than RB, the effect of RB on V in can be ignored. Why we ignored RB here? in our calculation of this V in, we ignored RB here because beta into RE dash will be much lesser. So, whenever a very less resistance value is in parallel with a very high resistance value, the effective resistance will always be lesser. So, we can actually ignore the effect of RB on the gain. So, that way as beta into RE dash is much less than capital RB, the effect of RB on V in can be ignored. It can be concluded that smaller the RE dash, larger is the voltage gain, and at the same time lesser is the input impedance. Look at this. If this RE dash is smaller, denominator is lesser. When the denominator is lesser, voltage gain can be larger. But at the same time, if RE dash is smaller, beta into RE dash also will be smaller. So, input impedance also will be lesser. That's why I told you all the ideal characteristics which we expect from an amplifier, we will not get it in any one particular circuitry. That is why later on we go for cascading of the amplifiers, where we connect many such amplifiers in series so that we get all the characteristics from all of them. Okay. Now, similar to base bias, we can have this voltage divider bias. Now, look at this voltage divider bias. R1 and R2 are the DC counterpart. Now, as far as the AC ground is concerned, we can write it this way. Capacitor is short, and I had told you about the DC bypassing capacitor at the emitter. Now, as far as the AC signal is concerned, whatever signal is coming at the emitter will be shorted to ground. So, here we can directly connect the emitter to ground because of this capacitor which is in parallel. And this blocking and coupling capacitors we are replacing with short. And the power supply we are replacing with ground because it is a AC ground. Now, this is the AC equivalent circuit for the complete voltage divider bias amplifier circuitry. Now, for this AC equivalent circuit, we have V in at the base, then R1, R2. You can see R2 one end is grounded, R1 one end is also grounded, RC other end is also grounded. Then we have RL. We can replace the transistor by means of this beta into RE dash and then IC. We can use the pi model. Now, for this AC equivalent circuit, if we write the pi model, how it looks like, let us see. If we write the pi model now, using the pi model, the voltage divider bias equivalent circuit is V in, and that is in parallel with R1, parallel with R2, parallel with beta into RE dash, and at the output side we have IC, current source, then we have RC, then we have RL. So, we can simply write the equation for the input impedance as R1 parallel with R2, parallel with beta into RE dash. In our earlier case of base bias, we only had RB. Now, here we have R1 parallel with R2. At the output, we can simply write the output impedance as RC parallel with RL. Please note here, even though we had RE here, that RE gets shorted by this capacitor because of the AC ground concept now. So, this is our equivalent circuit. So, we can simply write Z in equals R1 parallel with R2 parallel with beta into RE dash, and we can write Z not equal RC when RL is not given. When RL is given, we can simply write Z not equals RC parallel with RL. Now, we can find out the expression for voltage gain. AV is V out by V in. V out is nothing but output current into output resistance, that is IC into RC parallel with RL. V in is nothing but IB into beta into RE dash. As I had already told, this beta RE dash is much smaller in value. So, the effect of R1 parallel with R2 also gets reduced here in the case of voltage gain. So, we need not consider R1 parallel with R2 when we calculate the voltage gain. So, it is IB into beta into RE dash. Again, IC is beta into IB. Beta gets cancelled. IB gets cancelled. We will get RC parallel with RL into divided by RE dash. So, this is going to be our equation. Now, let me stop sharing this PDF and let me start sharing the PPT where I have the exercises. Okay, let me quickly go through whatever I discussed till now. Whatever I put it in the notes, briefly I have put it in the PowerPoint as well. This is called as RE model by Boyle-Stud. Whatever is the pi model called by Malvino is the RE model called by Boyle-Stud. So don't get confused here, both are one and the same. There, Malvino specifically uses a symbol Re dash just to indicate that is the internal resistance of the emitter. Whereas Boyle-Stud simply calls it as Re itself because it's the dynamic resistance of the emitter. So that way there are different styles in different books, but it is one and the same. So let me proceed. This is the transistor, and for the transistor I had already told you about the T model. We represent it by a current source at the top and by a diode here from base to emitter. And that diode we represent by means of emitter resistance, and we have a beta IB there. This is nothing but the T model. The T model can be written as a pi model now. Here Zi is Vi by IB and Vi is nothing but VBE by IB. For this particular circuit, Zi is VBE by IB. VBE is IE into RE, that is nothing but 1 plus beta into IB into RE. Therefore, Zi for this circuit itself is 1 plus beta into Re. That 1 can be ignored. We can write Zi as beta into Re. This itself is the discussion of my earlier class where I told that the input impedance of the transistor itself can be represented using beta into Re. Okay. So this VBE by IB, there IB gets cancelled, then we have this beta into Re. Now this can be represented, this particular expression itself can be represented as a beta into Re at the input side and beta into IB at the output side. This itself is the pi model, also called as Re model. You are already familiar with this, so let me proceed to the next slide where we have the computation of the input impedance for the base bias. Now the direction of currents indicate 180-degree phase shift here. You can see that IB is going into the base whereas IC is going into the collector, and when we represent using this pi model, IB and IC are in opposite directions, which simply means that there is a 180-degree phase shift. When IB is increasing, IC also will be increasing, but it will have a negative sign because it is in the opposite direction. So we are going to use a negative sign in future just to indicate this 180-degree phase shift. Okay, before going to the exercise, let me tell something about the output resistance, which I did not discuss in the notes. And this is specifically discussed in the particular book Boyle-Stud. There is something called early voltage. Early voltage does not mean early voltage and late voltage in English language. Early voltage simply means it was discovered by James Early in 1952. What is the meaning of early here is, it is a surname. Okay, don't get mistaken that there is some early voltage or late voltage. That voltage is named after a scientist called James Early, who studied BJT exhaustively. Now let me tell what is this early voltage. We have this output characteristics of the transistor, and for a given base current we can find out the output resistance at the output resistance as delta VCE by delta IC for a given slope. But here you can see for each value of IB that resistance is going to change because the curves are not identical always. Now should we consider the output resistance of the collector to emitter junction or not is the criteria now. In our earlier discussion, we only considered the collector resistance RC and load resistance RL. We did not bother about the internal resistance of the transistor between collector to emitter. Should we consider or not is the question now. So for deciding this, James Early made an experiment with the transistor. What he found out was that all the lines here at the output, if their slope is turned towards the left side here, and if all these lines they are converged down, all the lines will join at a point called VA. This is what James Early discovered. That means even though the transistor is working at different base currents as such, and even though all these output curves have different slopes, all the slopes can be joined by a straight line and dramatically or to be truly, all these lines are going to join at a point called VA. Now, the total resistance, total voltage at the x-axis can be VA plus VCEQ, where VCEQ is the Q point. So, if at all you consider this, VCEQ is much lesser compared to the total voltage VA. So, should we consider the individual resistances here of each curve, or can we make it as an average because VA itself is much larger? That is when James Early made a discovery that we need not consider the individual slopes of these lines. We can ignore the effect of IB on the output resistance as well, because VA is much larger than VCEQ. That is his discovery. So based on this, we can write the expression for the output impedance R0 for the transistor. I am not talking about the complete amplifier. I am talking only about the transistor now. So R0 is delta VCE by delta IC. That is what is shown here, right? Now, this R0 is delta V by delta I. Now, considering the discovery of James Early, R0 is VA plus VCEQ by ICQ. Now, we can conclude that R0 is approximately equal to VA by ICQ, because VCEQ is much lesser when compared to VA. So, we can approximately say R0 is VA divided by ICQ. In general, what happens is, this value of R0 will be given by the manufacturer himself. We don't have to find out the early voltage for each given BJT. ICQ we will be knowing. VA we need not know, because R0 will be directly given by the manufacturer himself. Now, at times what happens is, larger the output impedance, lesser will be the loading of the next stage of the design. Which means, let us say we are going for a multi-stage amplifier where we connect each stage to the next stage to the next stage. Please recall the things which I was telling you, that we will have a pre-amplifier stage, we will have a middle gain stage, and we will have a power amplifier stage in general. Otherwise, we will have many stages at the middle between the pre-amplifier and the power amplifier, so as to achieve larger gain and so as to achieve all the ideal characteristics which I mentioned earlier. So, in such a case, larger the output impedance for a given pre-amplifier, lesser will be the loading of the next stage of the design. Now, don't get confused with the statement which I told you earlier, that ideally an amplifier should have a very low output impedance. Ideally, if the amplifier is single, then we expect a very low output impedance. Here in this case, we are discussing about the cascading or the series connection of the amplifiers. So, in such a case, if the pre-amplifier is having a larger R0, then it is better for us, because it will have a lesser loading for the next stage of the design, because in the next stage we have one more amplifier which is supposed to have a very high input impedance. This output impedance itself is going to work as an input impedance for the next stage. So, in such cases, we want a larger value of R0. Now, with this discussion, let me proceed. We have already seen this particular circuitry, where now we include this R0 at the output. Beta RE along with beta IB, and we add this R0 which indicates the output resistance between collector and emitter, and beta R is the input resistance between base and ground. Okay, emitter is anyhow grounded. This is nothing but the RE model now. Whatever you called as a pi model, for that pi model, Boylestad adds this R0 and he calls this as RE model simply. Now, as I have already told you, the small re is nothing but kT by Q divided by IE. This kT by Q is nothing but thermal voltage Vt by IE. So, at 27 degrees centigrade, small re is 26 volts divided by IE. The RE model for a common base configuration is what? For the common base, here it is base to emitter. We are considering a PNP transistor for easy discussion. We have a base to emitter, then we have a collector to base. Base is common here, so emitter to base and collector to base, because this is common base. So when it is common base, at the input we have the diode directly there. So we are simply replacing this whole thing by Re. We are replacing this diode, and the output current is in the other direction. Converse to the common emitter configuration, here current is in the other direction, which means that there is no 180-degree phase shift. In common emitter configuration, there is a 180-degree phase shift between output and input. Whereas in common base configuration, there will not be any 180-degree phase shift. Why? When the emitter current increases, even the collector current is increasing. So they are in phase. Okay, and they are flowing in the same direction. That way, in the common base configuration, there is no phase shift. So now, using this particular symbolic diagram, we can write the RE model for the common base configuration directly like this. This diode itself is replaced by Re, because at the input there is emitter and base. So that is replaced by the emitter resistance. And at the output we have IC. IC is nothing but alpha into IE. In the earlier configuration, we used beta into IB because it was common emitter. In this case, it is common base. So IC is alpha into IE. Then we already have this R0. So this is the equivalent circuit of transistor for common base configuration. Using these two models, we are going to have some exercises now. Now this is the AC analysis of the fixed bias CE, common emitter. I had already shown you in the notes. I am quickly going through it. RB with respect to ground, RC with respect to ground. This transistor we replace with pi model or the RE model. So we can simply write that at the input side, Zi is RB parallel with beta RE, as I already told. At the output side, it is Z0 RC parallel with R0, because we have included R0 here now. RC parallel with R0. So voltage gain is V0 by Vi. We are putting a minus symbol because of the sign of the currents which are in opposite direction. So minus beta into IB into RC parallel with R0 at the output, divided by beta into RE into IB at the input. We are always ignoring the effect of RB because beta RE is very less when compared to RB. So we can find out the voltage gain. So AV, beta gets cancelled, IB gets cancelled. AV is nothing but V0 by Vi is minus of RC parallel with R0 divided by small re. Let me have a quick exercise now. For this particular circuit, find Zi, Z0 and AV. So, let us apply the formula. We have to find out Re first. For that, we have to find out IB first. Please recall the DC analysis. IB is nothing but VCC minus VBE divided by RB. 12 minus 0.7 divided by 470K, that is 24.04 microamps. When IB we obtained, we can obtain IE. IE is nothing but 1 plus beta into IB. Beta is given as 100, 1 plus beta into IB is nothing but 2.43 milliampere. Once we get this IE, we can find out small re. That is 26 millivolts divided by 2.43 milliamps. We are getting this small re as 10.7 ohms. This is the dynamic resistance of the base to emitter junction. Now, we will substitute this for finding out Zi. Zi is RB parallel with beta into Re. RB is 470K, 10.7 into 100 is 1070. You can see input impedance is 1.07 kilo ohms here. Even though RB is 470 kilo ohms, we are getting the input impedance much lesser. That is why that RB is ignored. Now Z0 is RC parallel with R0. Manufacturer has given the value of R0, that is 50 kilo ohms. RC is nothing but 3 kilo ohms. 3 kilo ohms parallel to 50 kilo ohms, we are getting 2.83 kilo ohms. And voltage gain is minus of RC parallel with R naught divided by this beta RE divided by RE. So minus 2.83 kilo ohms divided by RE is 10.7. So we get around minus 265. Now look at these three values. Input impedance is around 1 kilo ohms. Output impedance is around 3 kilo ohms, whereas voltage gain is around 265. Which means the base bias circuit is having a good voltage gain. Voltage gain is 265 times. Means if you give the input 1 millivolt, you will get the output as 265 millivolts. That is a good gain. But look at the input impedance. Input impedance is supposed to be very high. No, it is not so. It is actually low. It is only 1 kilo ohms. Output impedance is supposed to be very low. No, output impedance is now very high. But if at all we connect a series connection of amplifiers, this is fine now. If at all we use this circuit as a pre-amplifier, then we need not worry much about output impedance because we are not going to directly connect our load to this circuit.